Alright, the ransom note problem. Given an arbitrary ransom note string and another string containing letters from all the magazines, we should write a function that will return true if the ransom note can be constructed from the magazines, otherwise it will return false. Note that each letter in the magazine string can only be used once in our ransom note. So, we have the first example in which we are trying to obtain the string AB, and all the letters from the magazines are AA. Definitely we can't do that, that's why we return false. And why is that? Well, we need the character A. And as you can see, we have two character A's, so we can use one of them. Let's say we use this one, everything good. But then we need to have the character B, which is not part of the magazine strings. So this is why we return false. Now, the second example, the ransom note is AA and the magazine is AAB. This is true. This can be achieved. We have the first character A. We are going to use the first A. And the second character A. We are going to use the second A. And here we got our ransom note string. So, this problem is pretty straightforward. We have to make sure that for each and every letter in the ransom note, we have at least one correspondent letter in the magazine. And in order to do this, we just have to count for how many times each letter from A to Z appears in the ransom note, and then for how many times each letter from A to Z appears in the magazine. Then, once we have these frequencies, all we have to do is check that for each letter, its number of occurrences in the ransom note is less than or equal to the number of occurrences in the magazine. For example, here, we have only the letter A with frequency 2, and in the magazine, we have the letter A with frequency 2 and the letter B with frequency 1. So here we can suppose that the letter B has frequency 0, the letter C has frequency 0, and so on and so forth. And here also the letter C frequency 0, D frequency 0, and so on and so forth. Now, if we take each letter from A to Z and compare the frequencies, what will we get? The letter A has a frequency of 2, which is less than or equal to the frequency of the letter A in the magazine. Cool. This means that for every A in the ransom note, we can find a correspondent A in the magazine, which will be placed in the string. Awesome. Now, B has frequency 0. This B has frequency 1. Again, 0 is less than or equal to 1, so even if we don't need any B, this property is still satisfied, and so will be for the other characters. As simple as that. In the first example, in the ransom note, A has a frequency of 1, and in the magazine, A has a frequency of 2, less than or equal to, everything fine, but B has a frequency of 1 in the ransom note, which is greater than the frequency of B in the magazine, which is 0. So definitely here, we can conclude that it can be done and return false. So all we need to do is get the frequencies of the letters in the first string, and then also in the second string, and then just compare the correspondent frequencies, and that's all. As we know from the previous chapter, whenever we want to count for how many times a value appears in some collection, in our case, a specific letter appears in a string, we can use frequency arrays or hash tables. But in this problem, because the number of letters in the alphabet is 26, there is no point in using the hash table. We can use one frequency array of size 26 to count how many times each letter appears in the ransom note, and also another frequency array for the magazine. And that's all. Let's see how the code looks like. And here is the code. What I do is that I first declare two arrays, number of occurrences 1 and number of occurrences 2, which are going to be our frequency arrays. First one, it will be for the ransom note, and the second one for the magazine string. And both of them basically have size 26 and are initially filled with zeros. Then I have to compute for how many times each letter appears in the ransom note and then in the magazine strings. So first, I take each character C in the ransom note string and I just increment the number of occurrences 1 of C minus the character A. And now you're probably asking yourself, why did I do this subtraction, right? why didn't I just write number of occurrences 1 of C plus equals 1? Well, I could have done this if I used the hash table and the pairs inside the hash table were characters and integers, right? So the keys were characters, and because C is a character, this is allowed. But since I work with frequency arrays and the keys are the indices, which are integers, this C is not a valid key. So what I need to do is convert the character C into an integer, which is also between 0 and 25. In order to do this, I make this subtraction, and what happens here is that the computer sees that, alright, I need to make a subtraction between two characters. And because subtraction is not allowed between characters, that doesn't make any sense, right? The computer subtracts the ASCII codes of these two characters. If you don't know what an ASCII code or what the ASCII table is, don't worry, it is just a way in which the computer maps each possible character that it can encounter to an integer. So, the ASCII code has a total of 256 characters, I think, or even more than that. But what's important here is that the letters appear one after each other. So, for example, the ASCII code of the letter A is 97. The ASCII code of the letter B is 98. Letter C, 99, and so on and so forth. The ASCII code of the letter Z is 97 plus 25, 122. The ASCII code of the character C, which we know for sure that it is a letter, will be an integer between 97 and 122. When we subtract the ASCII code of the letter A, which is 97, from that number, we are going to get a number between 0 and 25, right? So what's going to happen is that if the letter was A, this subtraction will give us 0. If the letter was B, this subtraction will give us 1. If it was C, it will give us 2, and so on and so forth. If it was Z, it will give us 25, which is perfect. This subtraction returns us the index of that letter in the alphabet when the alphabet is, of course, 0 indexed. This is exactly what we need here. So I do this for the ransom note string, then I do this for the magazine string, but this time I count them in the number of occurrences 2 frequency array, and after that I take each and every index from 0 to 25 and I compare number of occurrences 1 of I with number of occurrences 2 of I, and if the first one is greater than the second one, I know for sure that our ransom note string cannot be obtained, so I return false right away. When this for loop finishes execution, it could have finished in one of two ways. Either from here, if we return false, or naturally, if we have checked each and every character and everything is fine. So, if this line of code is ever going to be executed, we know that it will be executed because we exited the for loop naturally. Think about it. If we exit through here, return false, we actually exit the whole function. So we won't even get here. And this is it. Now, let's analyze the time and memory complexity of the algorithm. In these two lines, what I basically do is allocate 52 integers. Now, 52 is an integer that is pretty small, so we usually say that this is big O of 1, but I'm going to share a secret with you right now. We actually have a notation for the number of letters in an alphabet, and that notation is called sigma. It's a Greek letter, and it looks like this. So, the interviewer, trust me, is going to be very happy if you know this and you say to him that the time complexity and also the memory complexity of these two lines of code is big O of sigma. Then we iterate through each character in the ransom note string. So this is big O of n. If we denote the length of the ransom note string by n, this obviously is going to be constant. So I have a big O of n from here. Now here, again, iterate through each character in the magazine. So if we denote the length of this string by m, and given that this line of code is also constant, this piece of code will be big O of m. And then we iterate through every number from 0 to 25. This comparison is of course constant, the returns are constant, so also this piece of code will be big O of what? Well, I can say big O of 1 because I have 26 iterations, but now that we know the definition, we can say big O of sigma, right? And as I said, this is constant. We get the time complexity of adding all of this together. So it will be big O of n plus m plus sigma. Big O of n plus m plus sigma. And this is it, guys. I hope you enjoyed it, and I'll see you on the next one. Bye.